So our next several lessons are going to be about differential equations. In fact, all the lessons this week are going to be about differential equations, and the lesson today is about verifying a solution to a differential equation. So first I wanted to review things that we knew about from before regarding differential equations. So remember that a differential equation is just any equation that involves the derivatives of a function. So if you see an equation that has derivatives in it, it's a differential equation. The solution to a differential equation is any function that satisfies that differential equation. Now, you may be curious as to what I mean by satisfies the differential equation. It just means that when you plug those things in, it works. The best way for me to show you that is to just go through an example. So suppose I asked you to verify that y equals e to the kx is a solution to the differential equation. And the differential equation I'm going to give is y prime equals k times y. Right? So first of all, take a moment to make sure that you believe me that this thing is a differential equation. Right? Well, I said up above that a differential equation was an equation, has an equal sign, that involves the derivative of a function. Right? So this thing simply says that the derivative is equal to some constant k times y. So the way that I verify that this thing is a solution is sort of by, starting with that. Y equals e to the kx. Right? Now let's figure out what y prime is. Y prime would mean the derivative of that thing. Right? So we know that the derivative of this should be e to the kx, and then the chain rule tells us times the derivative of whatever was inside. Well, the derivative of kx is k. Now what I'm going to do here is I'm going to take this stuff and I'm sort of going to plug it into this equation and see whether or not it comes out true. And so let me sort of use color to indicate this. So if I think about y prime being in green, I'm going to put that here. And if I think about y being in red, I'm going to put that here. And the question is, when I plug those things in, am I going to get a universally true equation? Right? So first, using the green, if I have e to the kx times k is equal to k times, and then y we said was going to be in red, y is e to the kx. The question is this statement universally true? Is it an identity? Oops. And it absolutely is, right? Absolutely. The left side of this thing is completely the same as the right side. So we verified that this function is the solution to this differential equation. If you're asked to verify that a function is a solution, all you have to do is plug those things in. So let's take a look at another example, right? What if I asked you to verify, let's make sure I'm using the right color, verify that, let's see here, what did I say? Y equals the square root of x squared plus 9 is a solution to the differential equation y prime equals x over y. If you've got time, I'd recommend you pause the video and try this one out. Take the original function, take its derivative, and plug those things in here. See if you end up with a true statement. You should, because I'm asking you to verify. So take a minute and do that. So assuming you just did that, you started off by saying y is, the square root of x squared plus 9. And you said the derivative of that, and we know the derivative of the square root of something is always 1 over 2 times the square root of that something. That's something I recommended that you guys memorize. But then the chain rule times 2x. In other words, y prime is, these 2's are going to cancel out, is x over the square root of x squared plus 9. Right? So I now have, my original function in red, which I'll put here, and I have my derivative, which I'll put here, and we're going to sort of confirm that this works out, right? So my derivative, x over the square root of x squared plus 9, that's supposed to be equal to x over the original function y, which was the square root of x squared plus 9. Those two things are absolutely the same, which means the function that I have is a solution to this differential equation. Marvelous. One last example. I sort of wanted to give one example where it didn't work. So I suppose I wouldn't use the word verify for this. I would say determine if y equals 3x plus 1 is a solution to the differential equation y prime equals xy. And again, if you've got 2 minutes, try this one on your own really quickly. If you tried this on your own, you found y equals 3x plus 1. That was given. So then we compute the derivative. Y prime is 3. And then I just plug these things in. This thing here, this thing here. When I do this, I end up with 3 equals x times 3x plus 1. And the question here is this an identity? Are these two things literally equal to one another? And the answer is universally no, they are not the same as one another. Now some of you might say, and I'll put this in red to indicate that it's sort of wrong reasoning. We could distribute. We could get 3x squared plus x. I could move the 3 over and do this. We could use the quadratic formula. We could solve this. But in the end, we would find out that this statement up here is only true for some quadratic formula generated x value. This statement is not universally true for all values of x, which means this function is not a solution to this differential equation. That's what it looks like just to verify. Hopefully this whole lesson was about us understanding what a differential equation is and what a solution is. The solution to a differential equation is simply a function that can be plugged in that will universally work. Right? That's all I have in this video. Well, I'll see you in the next one.